The next extension is actually very interesting. Okay, it's actually very different from the Voronoi diagram that we discussed earlier. Okay, we kind of will treat the next extension as like a complete new new problem. Okay, even though I mean some idea may still be common. Okay, that's so because as I say, I treat it as a new problem. So I will first motivate it with very interesting industrial engineering problem. Okay, in industry, okay, a lot of like mechanics, okay, a lot of like I mean when they create like certain parts, okay, for machines, okay, many parts require some kind of round shape object, okay, round shape object, okay, such as a ring, okay, ring. Actually, creating ring, okay, a good ring, okay, is a very important part in many branch of industry, okay. So because you can see like rings, I mean, in many machines, okay, as an important part, okay. But the issue is, okay, when a company when you buy a ring or a round shaped object from a company, you know, how do you know? How do you know if the product they create is good enough? How do you measure it? Do you say, oh, let me try to measure it by using, taking a photo and then, you know, try to use like, certain, it's a computer vision approach. It is possible, but obviously, if you want to do that, then pretty much for every like a batch of object the company deliver, you need to do similar job again and again, and a lot of these things, because it involves taking photo, it involves like a computer vision. If you it's not any easier, then you just create this ring by yourself, right? You can just create this ring by yourself if you know how to measure it very, accurately, right? So it's kind of like what should I say, like a tedious job, okay? Because this type of parts, the ring, okay, normally, okay. I mean, if you, as I say, it's a very common part in many machines. Okay, if you try to try to look into, for example, engine. Okay, you try to look into like what parts are used in engine. You will see like tons of rings. Okay, built by different materials. So those stuff it comes in, a large quantity. You just cannot do it you just have to have a good way to determine if this batch of ring are good enough, are round enough or not. Okay, so to do that, okay, mathematically, okay, normally we use sampling. Okay, the sampling concept has been used in many areas, including this type of stuff. Okay, so we can use sampling concept to measure the roundness of some rings. Okay, so how do we use the sampling concept in this case? Okay, it's like this. Okay, we first randomly, okay, put some dots. Okay, we can do that very easily, right? Keep in mind that, okay, these are rings, right? I mean, even though you may imagine ring as like a three-dimensional object, okay, but in reality, most of the rings, because they are used for like I don't know how to, I don't know the English term for that, 垫片. Okay, 垫片. Just like when you like a screw, screw something tight. Okay, you need some of those rings in between the screwdriver and the base. You know, those stuff, right? So if you really, I'm not saying like the ring you wear on your finger, okay? I'm talking about those parts. And because imagine those parts are actually flat, right? Those parts are flat. It could be very big, it could be very small. But the issue is, okay, because it's two-dimensional, so you can put like some sample points on the surface of the object very easily. Okay, this can be done relatively easy. Okay, so now you need to determine the roundness of a set of point P. Okay, we define it as the width of the smallest width annulus that contains the points. Okay, so if this ring is built very well, okay, it's very round and what should I say? It's a very thin. It should be very thin, like across the whole region, right? Very thin. Okay, then this distance, okay, the annulus, you know annulus. Do you know annulus? This term? Well, you just did a paper on that, okay? But anyway, like this annulus, I mean, basically means like this circle shape. And you measure how wide this thing is. Okay, that's what we call like we want to see like the width of the smallest width. Okay, annulus that contains the point. But you may have question. Okay, why do we say it's the smallest width annulus? It is because they are, I mean, we want the annulus that contains the points. So remember, we are not really measure the width from the edge. Okay, if we measure the roundness by the edge of this this object, then we don't need to do this sampling at all. Okay. The point of this sampling is to focus on only the sample points. We no longer look at the edge. We no longer look at the edge. I mean, here we draw these two circles. It looks to you like, oh, those two circles represent the edge of the object. No. Not at all. Not at all. Those points are on the object, but we do not know. We don't even draw the edge of the object here. Okay? So your question is, I believe, I mean, the first question that come up with you is like, how do we draw these circles? Right? because we consider ring, right? We consider ring. So these two circles, okay, those circles, first, those circles should include all these sample points in between these two circles, right? This is obviously the case, right? Okay, we need to first do that. The second thing, this is very interesting, okay? We need to make sure, okay, these two circles have the same center, obviously, right? Okay, so under these two constraints, okay, when you want to minimize this width, you can imagine there are three ways to minimize it. Okay, the first one, okay, you may feel like, oh, these three rings look the same, right? But actually they are different. Let me point it out. Even though just by looking, they look the same. They look the same width as well, but actually not. Okay, it's because the difference is too tiny that you cannot see. But let me point out the difference of how these three figures are drawn. Okay, the first one, take a closer look. 3 points determine a circle, right? 3 points determine a circle. Everybody knows that, right? So first, you can see, we try to draw the circle that sort of go past the three furthest points. You see, 1 point here, 1 point here, 1 point here, right? And then once we determine this, use this three furthest point to determine the circle, then we know the center, right? And then from the center, we can try to, expand it until what? Until we hit a point. We hit a point here. Because remember, we want to include all the points in between these two circles, right? So if you use the three furthest point to determine the center of the circle, then you sort of use like a nearest point to determine the inner circle. Okay, so this is how the first figure is drawn. How about the second one? Second one is you try to find the three nearest points. You can see here, here, and here. So you try to find these three nearest points to draw the inner circle first. And once you have the center, you try to find the furthest point from this center to draw the outer circle. So you can see this outer circle only past this point. Right? Right? So these two are drawn differently, right? Now you can see that, right? How about the third one? The third one is very tricky. Okay, now it's kind of like you have moving target. You use 2 furthest point and 2 nearest points. Okay, 2 furthest point to draw the outer circle and 2 nearest point to draw the inner circle. But now, okay, with the constraint, they need to be at the same center. You can see the outer circle go past 2 points, right? The inner circle go past 2 points. But these 2 points are not chosen arbitrarily because the outer circle and the inner circle need to share the same center. Okay, so obviously, you have these 3 ways to draw this annulus, right? And then whichever give you, actually, you should use the one that with the smallest, that provide the smallest width, and use that as like an indicator to see how how well this batch of product is, because eventually you want to measure the roundness of these rings, right? So this is the idea how we use sampling technique to measure the rings. Is it okay? So far so good. Are you guys still following me? So the next question you have, maybe, what does this to have anything to do with Voronoi diagram, right? Okay, it doesn't look at all like a Voronoi diagram, right? Okay, so here comes the interesting part. Okay, so finding the smallest width annulus is equivalent to finding its center point. Okay, if you know the center point, okay, obviously, like you can use the shortest distance, the closest point and the furthest point to determine the annulus, right? So the point is like the center. The most important point is the center. I mean, in the first case, we use the 3 furthest point to determine the center. The second case, we use the 3 nearest point to determine the center. The third one, well, it's a kind of moving target, but we need to make sure the outer one, inner outer circle and inner circle, they all go past 2 points, okay, to have the same center. Okay, so that's, if you try to do this computation, you will understand. I mean, it takes time. Why? Because, well, you need to check, like for every 3 point, you try to, well, if you are able to do some computation. Because remember, I mean, you are only given these points. You don't know, I mean, now you feel like, oh, we just find out like some points to consider, right? We should find like a nearest point to consider, okay, for example, or like a furthest point to consider when we want to consider 3 points. But when you are just given those points, I mean, without those outer circle, inner circle, I'm sorry, without those outer circle, inner circle, you really don't know which point is outside, which point is inside. Sometimes it's very difficult to tell. So I mean, the easiest way is C3-2, right? C4, CN3, right? Sorry, CN3. You just get 3 points, and then use those 3 points, okay, to consider the center, and then check if the center works for you or not, right? For first 2 cases. Just the first 2 cases. I mean, CN3, I mean, what is the complexity? Order 3, right? Order will be 3. Not to mention, okay, the last one, wow. How do we do? It involves solving equations, right? It involves solving equations. It looks complicated, right? So we need a better way to determine it, right? I mean, if you directly consider like what should I say, like high school geometry to solve these problems, then the situation may be even worse than, you directly consider the edge, how round the edge is. Okay, it may be even worse than that. So we need a good way to think about this. Okay, so finding the smallest width annulus is equivalent to finding the center point. We know that. But once the center point Q is fixed, the annulus is determined by the point of P that are closest to and furthest from Q. I mean, this is obvious, right? We know that. Okay, so if we have the Voronoi diagram of P, then the closest point is the one in which cell Q lies, right? Okay, so actually, okay, let me try to explain the middle case a little bit closer. Okay, if you try to draw the Voronoi diagram, this center obviously has a circle event, right? Because it has a largest center that goes through these 3 points without any point inside, right? This is obviously a circle event, right? So that represents what? That represents the center point will be a vertex, in the regular Voronoi diagram, right? Right? So far so good, right? For this one, well, we only know the center will be on certain edge, on an edge of Voronoi diagram, right? That's it, right? But we don't know which point. Okay? Here comes the interesting part. Okay? How about this? We say, oh, then this will be, well, this goes through 3 points, but will include all the points. Well, this is not Voronoi diagram, but what is this? Okay, so here comes the interesting part. Okay, we can define a similar structure, okay, for the furthest point, okay, which is called the furthest point Voronoi diagram. Okay, so a point, okay, a point in a cell belongs to a site if and only if that site is furthest from that point compared with any other site. Okay, so this is exactly the opposite of the regular Voronoi diagram. Okay, because in the regular Voronoi diagram, we consider the nearest site, right? Now we try to consider the furthest site. So this is very different. Okay? So, if we try to consider the furthest site, then you could imagine, we haven't had the solution yet, okay? But assuming we are already able to create the furthest point Voronoi diagram, then you can imagine the center for this one will belong to the furthest Voronoi diagram of these 3 sites, right? So it will be what? It will be obviously a vertex in the furthest point Voronoi diagram, right? Just like the middle one, right? It's a vertex in the regular Voronoi diagram, right? And for this one, it will be, the center will be at the edge, at a certain edge of furthest point Voronoi diagram, okay, for these 2 cells, shared by these 2 cells, okay, for the similar reason. Okay, so now, okay, so if we are able to solve the furthest point Voronoi diagram quickly, then we should be able to do this thing, to solve this problem quickly, right? So now, okay, so let's consider the furthest point Voronoi diagram. So let's officially define this problem. Given a set P of points in a plane. So now, okay, let's confine. Okay, this is different from the previous extension. We only confine point sets. Okay, point sites. We don't consider point sites. We don't consider segments. Okay. Okay. So given a set P of points in a plane, a point of P has a cell in the first point Voronoi diagram, if and only if it is a vertex of the convex hull of P. So this is a very important observation. Okay, why is that? Sorry. Let's say we have a Voronoi diagram. We don't know what its shape is, okay? And we have another point, okay, somewhere in the middle. Okay, and then we use a proof by contradiction. Okay, if this point, okay, this is a side. If this side has a cell, for first point Voronoi diagram. So let me change the. If this point has a cell, say if that cell, I just obviously draw. If that cell belongs here. Anyone? Okay, it's better. So if the cell belongs here, then we just pick any point here in the cell. I draw a line segment. Oh, my drawing is terrible, but you get the idea. Okay, I draw a line. Okay. Because this is a direct line. Okay, if such a cell exists, I can find a point, right? And this point, according to the first point Voronoi diagram, this point should be, the first side from this point should be just this side, right? The other side should be closer to this point than than this one, right? But obviously, when you try to draw it, you can easily extend, because this point is not in the Voronoi diagram, right? It's not part of convex hull. This point is not part of convex hull, right? So you can extend. You can extend this line segment. You can extend, okay, this line segment. The extension of this line segment must intersect the Voronoi diagram, right? Right? Okay. And then, okay, it may intersect an edge or a node in the Voronoi diagram, right? Right? If it intersects a node, say this is a node in the Voronoi diagram, obviously this node, okay, this node is one of the sides, right? So this node obviously is further away from that point than this one, right? Than this S. Okay, this is P. Okay, if this is a side, this side is further away from P than this side S, right? Then we have a contradiction, right? Right? But if you say, wait a moment, it doesn't have to be the intersection doesn't have to be a side, right? How about it just intersect a line segment? That's fine. If you intersect a line segment, okay, let's consider, okay, the two endpoint, okay, let's call this one like a A1, A2, okay? A1, A2, A1, A2, A1, A2, okay? And, well, we can consider either of them, okay? Maybe say like a A1, S, P, this triangle. Because, obviously, this A1 or A2, it will be, away from S, right? Okay, so this angle will be greater than 90 degrees, right? This angle will be greater than 90 degrees, right? And remember, A1, A2 are both sides as well, right? So again, you can easily find a side which, you know, is further away from S than, further away from P than S. Okay? So either way, okay, I mean, if a side is inside convex hull, it shouldn't be included in the, it shouldn't have a cell. Well, it shouldn't have a point. It shouldn't have a point in the farthest side, farthest point involved in the diagram. Not to mention a cell, right? So it's just this is like obvious to you, right? So based on our proof, okay. So we know not all points have cells in first point involved in the diagram. So this is the first important observation you guys need to understand. Okay, so after this one, okay, obviously, I mean, to consider the construction of the farthest point involved in the diagram, the first thing is what? The first thing is to try to, you know, create the convex hull, okay, for the given n sides, because only the point that contribute the convex hull, the outside, will need to be considered. I mean, when you construct the first point involved in the diagram, anyway. Okay. So this is I mean, first thing. The second thing, the vertices and edges of the farthest point involved in the diagram form a tree-like structure. Okay. First, they are connected, obviously. Okay, but why is it a tree-like structure? Okay, because the diagram is connected. Okay, but it does not have a cycle. Why does it have no cycle? Okay. Say, if you have some cells, okay. If you have some cells that are connected and form a loop, what happens is that, okay, so this cell is a farthest side involved, I mean, is a cell involved farthest side involved diagram. Same as this one, this one, this one, this one. But how about the middle, the center that is surrounded by this, you know, by this loop? I mean, this farthest side Voronoi diagram, I mean, should partition the two-dimensional plane, right? Just like a regular Voronoi diagram, right? Okay, those cells should partition the two-dimensional plane. So you must, these center pieces must belong to some nodes as a farthest side Voronoi diagram, right? But obviously, I mean, when you consider this, I mean, if this one belong to a side here, let's say this is S, okay, so any point, say point P belong to this S, side S, okay, then what happens is that, okay, obviously this S is not part of this sides that surround P. Obviously, otherwise, I mean, this region will be included, right? If this one is a cell for S, I mean, and P belong to S, I mean, obviously this cell should, like, you know, should include that point already, right? Right? So you say, oh, this S, okay, maybe like, okay, so we have another side here, okay, that contribute, because it's first, this side should be here, okay, because, okay, let's say this is S prime. S prime contribute this side, okay. Then, okay, what happens is that you have P, you have this, the selection of this is not very well, okay. You get it's this. Let me see. Yeah, so look at here. So if you say, okay, this one is furthest from S, okay, and then this node contribute this one. That include S. Then let me see. S. I probably should have considered. Yeah, I mean, I shouldn't use this one. I use the other one. Should be here. Okay. It's the other direction. Okay. So we know this may be a side S prime that contribute one of the, I mean, this is let me call it S1. S1, okay. That contribute to S1. Yeah, okay. So this, assume this is the cell for S1. This is a cell for S1. Okay. Then, okay, let's consider this one. And any point in this cell. Okay, assume S and S1. Okay, S1 is the closest side that contribute a cell. Okay, here. Okay, so because we know S is further away from S1, right? Again, we are proving by contradiction. Okay, we know S is further away from S1 than P, right? Then you can, sort of like draw a line, okay, that go past P, okay, to a point here. Then what we need to prove is that, okay, this line is further away from this line. Okay, it's further away from this line. to here, to S1. Okay, let me see. So this edge is larger than this edge. Okay, and then this edge plus this edge plus this edge. Something's wrong. I made a mistake here. Wait. It's 7 o'clock. If it belongs to side, all side. Okay. Yeah. Let me use a different way. And then we say, we draw a line, go past and then, okay. And then remember that in the previous result that we have proven, we have two. Okay. This F, okay, is original, is inside here. Okay, it's inside here. So it is surrounded, okay, there we have there, the side of quantity is there, the side of quantity is there, and so on. Okay, so if you try to draw a roller valve, a roller is try to circle this side. Okay, the S should be inside of this roller valve, right? Right? If I try to draw the let me go back here, okay, and because we are running out of time. I have to finish this one before before finish this chapter, before the midterm. So let's assume this is correct. Okay, I will come back to this before the end of the class. Okay. So the white, it doesn't have cycle, I will come back to discuss this. Okay. Because a cycle implies boundary cell. Okay. Oh, yeah. Okay. Because the cell cannot be bounded. Okay, I forgot to look at this. Okay. This is the boundary cell, right? This is the boundary cell. Okay. So if a side, okay, if a side contributes to that cell, that is formed, okay, then if this is boundary, okay, then we have problem. Why? Because in the solid form roller valve, every cell is unbounded. Okay? Because free boundary.
if this side, okay, it's not to show you, it has nothing to do. If this is the side, then contribute a particular point. This is a point P, or this is a point P, okay. That is inside a side, a cell of the side. Okay. We know, okay, PS distance is the furthest compared to any other side, right? It's already the furthest compared to any other side, right? Then, when you consider the straight line, when you consider any point, you try to show extended line. We call it P prime, okay? P prime has to belong to the cell in F, the cell of F. It has to belong to the cell of F. In other words, P prime, okay, the extension of this of FP, okay, any point in this extension will belong to this cell as well. Why? Because if there's another side, say, F prime, okay, that is further away from P than F. Okay, then okay, then P prime, F prime. Okay. Will be
P prime S prime will be smaller than thank you. Okay. P S prime plus P prime, right? I mean, in this triangle, two sides, the sum of two sides is greater than the third one, right? Okay, and then, okay, we know, okay, because P, okay, belongs to the furthest point, I mean from S, right? So PS, okay, must be, right? This distance must be further away than this distance, right? Right? Otherwise, P wouldn't be in the cell of furthest point Voronoi diagram cell of the side S, right? But these two add up to be SP prime, right? SP prime. So, well, P prime S prime is going to be smaller than P prime S. Okay, the distance. Right? So this is the way to prove it. I'm sorry. Okay. Sorry, take more time. Okay. So it cannot have a cycle because cycle will be a bounded cell. I mean, as I have drawn it. Okay. So farthest Voronoi diagram of n point, okay, has n has a linear number of vertices, edges, and cells. I mean, obviously, I mean, it has less or equal to a number of cells. That's obvious because only the Voronoi diagram vertices created by this endpoint will have cell, right? So, well, I mean, the worst case, I mean, is that all the endpoints contribute to the Voronoi diagram. So you have at most n cells, right? Otherwise, you have less than n cells, right? As for number of vertices and number of edges, okay, the proof will be similar to what we have for the regular Voronoi diagram. Remember, in a regular Voronoi diagram, we prove that it has a linear number of vertices, linear number of edges. Okay, to be obviously, I mean, to be exact. Okay, where is it? This one. Okay, if it has here. Okay, a Voronoi diagram. Okay, has 2k minus 3, okay, if it has k cells, it will have 2k minus 3 edges at most, 2k minus 3 edges in the first point Voronoi diagram, okay. So I mean, the proof will be similar, okay. I mean, actually, I think here I have told you like, yeah, exercise 7.14, which is actually a question I assigned in the homework for you guys, okay? So you can try to use similar way to solve this question, okay? So back to the this observation. So so this one, okay? I mean, as I said, vertices and edges. I mean, you can prove that. I mean, by yourself. For cells, this is obvious, okay? So then, okay, how do we you know, create an algorithm for that? Okay, well, can we take 5 minutes break? I'm a little bit tired. Okay, let me take 5 minutes break and then we'll come back to finish this chapter. Okay.